In this talk, I'm going to present the work Gaussian process model selection via Minibatch SGD, Convergence guarantees and empirical benefits. This work has been accepted in part to NeurIPS 2020. I'll start with the motivation and the problem formulation, and then I'll present the theoretical guarantees and empirical results we obtained. Finally, I'll conclude with some open questions. So Gaussian processes have been widely used in many areas as a flexible model for predicting unseen data and providing uncertainty quantifications for them. The key idea for GP is to assume a dependent Gaussian distribution as a prior over all samples, and then one can calculate the posterior distribution for any new data point given this prior and the observed training data. So in order to provide good prediction, it is crucial to choose the appropriate dependent structure in the prior distribution, which is encoded in these hyperparameters in the Gaussian processes. So in this talk, I'll focus on GP model selection, or you can also call it GP hyperparameter learning. And because of the computational challenges in GP problems, we will focus on how Minibatch SGD is going to perform for solving this problem of GP model selection. Okay, so now let me describe the formulation of Gaussian processes that we are going to work on. So the input data xi or the covariates are sampled IID from some underlying distribution P. The output data yi is generated from this regression function f and this additive noise term epsilon I. We assume this noise term epsilon I is sampled from this Gaussian distribution with variance sigma epsilon squared, which we'll call it the noise variance. We also impose our prior distribution over this function f, which is a Gaussian process with mean 0, and covariance function looks like this. So the covariance function is a kernel function k multiplied by a sigma f squared, the signal variance. Under this prior distribution, if we pick an arbitrary pair of input data xi, xj, then fxi, fxj is going to follow this Gaussian distribution with this covariance matrix. So if kxi, xj is a large positive value, it means that fxi and fxj are likely to be closer to each other. So that is to say, this covariance function in the GP model is going to encode our belief about what kinds of inputs are going to lead to similar outputs. Or you can also think of it as some sort of smoothness. So based on this prior distribution and the observed training data, one can always come up with a posterior distribution for this function, the regression function f. So like here in this figure, the left-hand side is the prior distribution, and the 4 solid lines are sampled from this prior, the Gaussian process with zero mean function. And the right-hand side is the posterior distribution given these 2 sampled observed data points. So the solid line here is the posterior mean given these 2 observed data points, and the 4 dashed lines are sampled from the posterior distribution. Okay, so for any new data point x star, we can also calculate the posterior distribution for that fx star, which should be Gaussian distribution. And the posterior mean should take this form, which can be used for prediction. Okay, so here this both symbol xn is concatenated by all the observed input data xi, and it is an n by capital D dimensional matrix. And this yn vector is an n-dimensional vector that is concatenated by all the output data yi. Okay, so what we can note is that this posterior mean for fx star shares the same formula as a predictor in kernel-ridge regression. So the only difference between these 2 Raed formulas is that we substitute this ratio between these 2 variance parameters, the noise variance and the signal variance. We substitute this ratio by the regularization parameter in the kernel-ridge regression, multiplying this number of samples n. So there is some sort of equivalence between this GP approach for prediction and also the non-parametric statistical model kernel-ridge regression. Okay, so they can both be used to providing prediction for unseen data. And from the GP perspective, if you want to perform good prediction, as I mentioned earlier, it is very important to choose the appropriate hyperparameters, such as these two variance parameters, sigma f squared, sigma epsilon squared, because these two are going to influence our predictors. And also, maybe we'll also want to choose appropriate parameters inside the kernel function K. So this is from the GP perspective. And from the kernel ridge regression perspective, this is equivalent to finding the appropriate kernel function or the reproducing kernel Hilbert space that we want to select our regression function f from. And also the regularization parameter lambda. So for solving these two problems, there are two commonly used methods in the literature. The first is cross validation, and the second is to minimize the marginal log likelihood loss under the GP framework. So both these two methods are widely used in the literature. The second approach is mostly motivated from a Bayesian perspective. I couldn't say which one is better because both are commonly used, but two advantages that I could think of for the second approach is that you don't have to specify a set of candidate hyperparameters that you want to select your parameters from, but instead you can just minimize the loss function over the entire parameter space. And furthermore, as we'll show later, SGD can provide a speed up for this optimization problem. So there is a computational advantage here. In this talk, I'll focus on learning these two variance parameters, sigma f squared and sigma epsilon squared. I'm going to learn these two parameters using this second approach. And we collect these two parameters into our two-dimensional hyperparameter vector theta star. So let's first check what the marginal log likelihood loss look like. So first we note that the output data yn follows this distribution, this marginal distribution. So it is still Gaussian distribution, and the marginal covariance matrix Kn theta star can be decomposed into these two terms. The first term comes from the prior distribution, and it is a kernel matrix that encodes all the dependence among all covariates, among all samples. So the formula for this kernel matrix looks like this, where each entry is the kernel function evaluated at one pair of sample data points. Okay, so the first part comes from the prior distribution, and the second part comes from the observation model, the additive noise term epsilon I. Because of the dependence among all these different epsilon i's, we have this identity matrix as a component. So the parameters we are interested in here, theta1 star and theta2 star, encodes these weights of these two covariance matrices when forming this marginal covariance matrix. We need these two parameters to tell us how to find the posterior mean for any new data point. Although here in this posterior mean, we only need the ratio of these two hyperparameters, if we want to provide some confidence regions or uncertainty quantifications, we need the exact values of both parameters instead of just the ratio. So here we focus on estimating both of these parameters together. Okay. All right, so based on this marginal distribution, we can write out the marginal log likelihood loss, which is this function L theta. We want to find the minimizer theta hat as an estimator for this theta star. So if we want to minimize this L function, this loss function using gradient descent, then at each iteration, we will need to calculate the inverse of this kernel matrix, the covariance matrix, Kn theta. So this Kn theta is n by n. So calculating its inverse is going to cost us n to the power of 3 computational complexity. That is inhibitive for many GP applications. In fact, the computational cost has always been a big concern in the GP community. So some recent paper shows that one can use the GPUs to accelerate the optimization problems in GP. And what they can do is to use 8 GPUs to fit 1 million data points in a few days, which is great. However, What we want to ask is, can we use SGD to further push this forward? This is a natural question because SGD has seen a lot of success in large-scale machine learning problems, and there have been a lot of theoretical and empirical study about how SGD is going to perform when minimizing this empirical risk function. So this empirical risk is mostly appropriate for independent samples because it is summed over all samples. However, there are much fewer results about how SGD is going to work under dependent settings, such as Gaussian processes. If we want to apply SGD to GPs, then the dependence among the GP samples is going to lead to the bias of the stochastic gradient with respect to the full gradient. In addition, the GP loss function is non-convex. I'll explain a bit more about these two challenges later, but these two challenges have inhibited the practitioners from using SGD in GP problems, even if they don't have enough computational resources. So we did some initial experiments, and it turns out that SGD can indeed perform reasonably well in terms of convergence. So that encourages us to think about some theoretical guarantees for SGD in GP. Okay. Now let me explain the challenges a bit more. So first, non-convexity. The second term in this loss function, which is the log determinant of the covariance matrix, is a concave term. The first term in this loss function is convex. However, it can be arbitrarily small due to the randomness of this data yn. Even if we substitute it by its expectation, this loss function is still non-convex outside of some certain region. Okay. The second challenge is bias. So we first write out these full gradients and the stochastic gradients. This Kc here is the set of indices formed by some mini-batch, and M is the size of this mini-batch Kc. The main difference between this full gradient and the stochastic gradient is that we substitute this inverse of this full covariance matrix K and theta by this inverse of an M by M submatrix of K and theta. So K Kc theta is the principal submatrix of this K and theta, and the rows and columns forming this K Kc theta is this mini-batch Kc. And why would this substitution give us some bias then? Okay, so to understand the bias, we can look at a special example. We can first look at the first entry of the full gradient and the first entry of the stochastic gradient. We can see that this first entry can be decomposed into two terms. The first is a trace term and the second is a quadratic term. We can first compare these first terms, these trace terms. What we know is that if the mini-batch size M equals to 1, then the expectation of this trace term in the stochastic gradient is going to involve only the diagonal values of the full covariance matrix K and theta. However, due to the strong correlations among the samples, this full covariance matrix K and theta is going to have a lot of non-zero off-diagonal values, which appear in this covariance matrix Kxn xn. So these off-diagonal values means that this expectation of this first term in the stochastic gradient is not going to be equal to the first term in the full gradient. So this is not a rigorous proof, but I'm just trying to provide some insight behind the bias. So when M is larger than 1, things will be a bit different, but the key idea is still the same. When you are using the trace of the inverse of a submatrix to approximate the trace of the inverse of a full matrix, you're always going to lose something. Okay. All right, so this is for the challenges. And before presenting our theoretical guarantees, I'm going to first introduce the minibatch SGD algorithm that we're considering. So this is our standard minibatch SGD algorithm. At each iteration, we first sample a subset of indices, which is of size M, and M is much smaller than the total sample size N. We can sample with or without replacement. It doesn't influence our theoretical guarantees. And the step size at the case iteration alpha k is going to scale as 1 over k. So we are having diminishing step size. The only thing I want to emphasize here is the scaling factor for the stochastic gradient that we are calculating. So first we can see the full gradient looks like this. So we can see there is an n in the denominator, which can be viewed as the scaling factor for the full gradient. One naive choice for the stochastic gradient is to consider m, the mini-batch size, as the scaling factor on the denominator. But as we will show in our theoretical results, sometimes it is better or it is more appropriate to consider some other scaling factors. Okay. So now let me present this theory that we obtained for Minibatch SGD. The first three assumptions that we consider are like this. The first two assumptions are the boundedness of the parameter iterates and the stochastic gradient. So we assume that the true hyperparameter theta star and the parameter iterates theta k at each iteration is going to be bounded within some region. And also, we assume that the stochastic gradient is going to be bounded at each iteration. So these two assumptions have been commonly seen in the literature on stochastic algorithms, but we do have some relaxation of these two assumptions. It is also okay if we just assume the boundedness of these true hyperparameter theta star and the initialization theta zero, because the boundedness of theta star and theta zero is going to imply the boundedness of all the other parameter iterates and also stochastic gradient. So that could be a sufficient condition for these two assumptions. But anyway, so the third assumption is concerned with the eigendecay of the kernel function k. We assume that the ith eigenvalue of k is scales as e to the power of negative bi, where b is the positive value that characterizes the decay rate. So if we have a larger b, it means that the eigenvalue of the kernel decays very fast and the correlations among samples are kind of weaker. So this exponential eigendecay assumption is satisfied by the RBF kernel, which is also called the squared exponential kernel. And this kernel function has been widely used in the GP literature. Okay, so under these three assumptions, we have the convergence guarantees for our noise variance. So this is the first convergence guarantee we obtain. And so the noise variance is sigma epsilon squared. So sigma epsilon squared is the variance of the additive noise epsilon I. And as the second parameter in this hyperparameter vector, it is multiplied by this identity matrix when it is forming this full covariance matrix of the marginal of the output data yn. So for this noise variance, we have this following result. If the scaling factor S2M is chosen as M, which is the mini-batch size, the naive choice, and if the initial step size is appropriately chosen, then with high probability, we have this convergence guarantee for the squared error of the noise variance. So there are two terms here. The first term is the optimization error. Capital K is the number of iterations, and this 1 over K error rate is the same as the convergence rate of SGD when it is applied to strongly convex objectives. But here we don't have strong convexity, but we still have this 1 over K rate. This is because a relaxation of strong convexity that the loss function satisfies. I will explain a bit more about this in our proof sketch that I will present later. And this gamma here is a constant value that can be viewed as a curvature. The second term is the statistical error term. M is the mini-batch size, and epsilon is a positive value that controls the probability term. Since this epsilon can be chosen really close to 0, we can think of this term roughly as m to the negative 1/2. So we do need the mini-batch size m to be somehow large in order to ensure the convergence. All right, so now let me explain the proof sketch for our first convergence result, and I'll describe how we address the challenges that I mentioned in the beginning. The first challenge we met is the dependence in the data. The dependent structure leads to the bias of the stochastic gradient with respect to the full gradient. To address this challenge, we consider concentrating the stochastic gradient around its conditional expectation given the sampled covariate, instead of concentrating it around the full gradient. And then we show that if we form the trajectory formed by this conditional expectation of the stochastic gradient, then we are guaranteed to converge to the true hyperparameter with 1/k rate. So here, the first step is going to give us a statistic error, and the second step is going to give us an optimization error. More specifically, at each iteration, we can decompose this squared error like this, which is very standard. And then we apply this lemma 1. So lemma 1 is the relaxation of strong convexity. G star here is the conditional expectation of the stochastic gradient given the sampled covariate evaluated at the kth iteration. And we see that the conditional expectation of the stochastic gradient, when it is multiplied by the difference between the parameter, between the noise variance and its true hyperparameter, this multiplication is lower bounded by the squared error multiplying some constant gamma. And there is a tolerance term here, log m over m, which converges to 0. So this lower bound here can help us provide a lower bound for this second term. And hence, we have a proper contraction when going from the k-1 iteration to the kth iteration, like this. Okay, so gamma controls our contraction rate. Okay, so by induction, we know that the squared error for the noise variance at the capital K iteration is bounded by this 1/k optimization error plus some statistical error. So here, this statistical error is EI hat, and it is the difference between the stochastic gradient G theta and its conditional expectation at the ith iteration. So to bound this EI hat, we use this lemma 2, which controls the difference between the stochastic gradient and its conditional expectation uniformly over all potential parameters theta. So this lemma gives us the statistical error, which is m to the power of -1/2. So this lemma looks very standard, but the proof is non-trivial. The main reason is that we have to show this bound uniformly hold for this all potentials theta. And also this stochastic gradient function G is highly nonlinear with respect to theta. So a direct covering argument is not going to work. Instead, we have to perform Taylor's expansion, and then we perform a novel truncation. Then a covering argument can help us get this uniform statistical error bound. Okay. Let me explain a bit more about this proof of the lemma 1 because it can provide us some insight about how the eigendecay of the kernel function is going to influence our theoretical result. So here we can first write out the left-hand side, the multiplication like this, which is the trace of the multiplication of several different matrices. And the trace term can be expressed as a function of eigenvalues like this. So lambda jk here is the jth eigenvalue of the kernel matrix formed by the kth minibatch. When the minibatch size m is large, we know that this lambda jk divided by m is going to be close to its population eigenvalue, which has this exponential eigendecay. So because of this closeness between the empirical eigenvalue and the population eigenvalue, and also the eigendecay of the in our assumption, we know that the first term scales roughly as a constant, and the second term scales as log m over m. So these two results give us this constant curvature term, and also this tolerance term, which scales as log m over m. If we have a different decay rates, then this tolerance term would be a bit different, and that is going to influence our statistical error rate. Okay. All right, so we also have the convergence guarantee for the signal variance, which is sigma f squared. Sigma f squared is multiplied by this kernel function in this prior distribution. And it is the first parameter in this hyperparameter vector theta. So it is multiplied by this kernel matrix kxn xn when forming this marginal covariance matrix kn theta for the data yn. For this signal variance, the convergence guarantee we have is very similar to the guarantee we have for the noise variance. The only differences are marked in red. We see that the scaling factor for the signal variance is constant multiplying log m instead of m. So that is different from the naive choice. And also the statistical error we have is log m to the power of -1/2 plus epsilon, which is much larger than the m to the -1/2 statistical error rate for the noise variance. So why would we observe such differences? This is actually because of the different matrices that these two parameters multiplied by. So more specifically, if we write out the conditional expectation of the stochastic gradient with respect to these two parameters, what we see is that the only difference between these two are these derivative terms. These two derivative terms. So k c theta is the marginal covariance matrix of the output data y in the mini-batch c. So this k c theta also forms this, also has this linear combination form. So the derivative of k c theta with respect to the noise variance is going to be the identity matrix. And for the signal variance, it's going to be the kernel matrix. As I mentioned earlier, the trace term here can be expressed as a function of the eigenvalues. And further, we can use that eigenvalue to provide the curvature for the parameters that we are optimizing over. So based on that idea, if we don't consider the scaling factor here, then the curvature for the noise variance is going to take this form. While for the curvature with respect to the signal variance, we have this form. So the identity matrix gives us this 1 on the numerator, while the kernel matrix kx c x c give us this lambda j squared on the numerator. So lambda jk is the j's eigenvalue of the kernel matrix formed by the case minibatch. So because of these differences, and also because of the exponential eigendecay, we know that this term scales as m, and this term scales as log m. So that is why we choose S1m to scale as log m, so that we have our lower bound for the curvature term with respect to the signal variance. Due to similar reasons, we also have larger statistical error for the signal variance. Intuitively, you can think that the stochastic gradient for the signal variance has a smaller magnitude than the noise variance. And that reflects that there is less information, statistical information hidden in the data about this signal variance theta1. So that provides some insight about why the statistical error for the signal variance is much larger than the noise variance. Okay. We also have some guarantees for the kernel functions with polynomial eigendecay. The polynomial eigendecay can make the kernel function extract stronger correlations among samples. So more specifically, the ith eigenvalue of this kernel function should be I to the negative b, and b is a positive value that controls the decay rate. This assumption is satisfied by the Matern kernel, which is also a widely used kernel function, a kernel class in GP communities. Okay, so for this type of kernel function, we also have similar theoretical guarantees. But we do need the decay rate b to be larger than this constant, so that the correlation is not too strong. And we have this similar guarantees for this case for noise variance. The only difference is that for the statistical error term, this epsilon here has to be larger than some function fb. Recall that for the kernel with exponential eigendecay, this epsilon can be arbitrarily close to 0. So that means the statistical error is basically m to the negative 1/2. But here, because this epsilon has to be larger than fb, when fb is larger than 0, we have a larger statistical error term. More specifically, in this plot, we have this fb. We can see that when b is larger than 3, then fb is negative. And when b is smaller than 3, we have our positive fb. So that means if b is larger than 3, we still recover the statistical error rate for the exponential eigendecay, but not the case if b is smaller than 3. Okay, I think that is just the price we pay for capturing a stronger correlation among samples. All right, so now let me present empirical results, including simulations and case studies. So in simulations, we generate the GP data from the GP formulation that we considered. And so we want to see how our minibatch SGD converges to the true hyperparameter. So we focus on the RBF kernel, and the total number of samples is 1024. The minibatch size M is 128. Here, these three figures on the top show the convergence of the parameter iterates when starting from 3 different initializations. For each figure, we have 10 different lines for each parameter, which are generated from 10 different replicates. What we see is that the noise variance converges very quickly to the true hyperparameter 1, regardless of different replicas or regardless of the initialization. However, for the signal variance, the point it converges to has a much larger variation across different replicates. This is actually consistent with our theory because our theory suggests that the statistic error rate for the signal variance is going to be log m to the negative 1/2 plus some epsilon, which is much larger than the statistic error for the noise variance. So our simulation is confirming this. We also checked the convergence of the full gradient. So I didn't present the convergence rate for the full gradient, but we do have this convergence rate provided in our paper, and the rate is the same as the convergence rate of the noise variance. So we would have 1/k optimization error and m to the negative 1/2 statistic error. What we see is that when the minibatch size m increases from 16 to 64, then the full gradient converges to 0 in a much faster way. So that suggests that the minibatch size, a larger minibatch size, indeed has a positive effect on the convergence. So that is supporting our theoretical finding. All right. So now let me present the second question that we investigate during the simulations. So in this second part, we want to see how the sampling scheme is going to influence our convergence result. We are interested in this question because in the GP literature, when people don't have enough computational resources, they usually would consider nearby sampling in order to reduce their computational cost and also preserving some reasonable predictive power about new data. This is very natural because nearby points is usually going to be more predictive than the points that are far away. However, that is for prediction, but here we are considering the problem of learning hyperparameters, so the effect of nearby sampling is not that clear. To investigate this problem, we consider this nearby sampling and we run some simulations. And it turns out that the noise variance is indeed converging faster when we are using nearby sampling than uniform sampling. But for the signal variance, it's converging in a much slower way. So that encourages us to think about the mixed sampling scheme. That is to say, at each iteration, we calculate the stochastic gradient for the noise variance using the data from nearby sampling. And for the signal variance, we calculate the stochastic gradient based on the data from the uniform sampling. And it turns out to be working reasonably well. So we think that mixed sampling is indeed a promising alternative to the other sampling methods. We also provide some heuristic argument about why this nearby sampling is giving us better convergence for the noise variance. I'm going to skip the details, but the key idea is just that when the sample points are closer to each other, the curvature parameters that which depends on the eigenvalues of the kernel matrix is going to be increasing for the noise variance. So that is going to give us our faster convergence when the samples are closer to each other, which is the case for the nearby sampling. We also conduct some case studies where we apply Minibatch SGD on some benchmark GP data sets. Because for these benchmark data sets, we don't really know what the true hyperparameters are, so we don't really consider convergence rate. But instead, we want to see how the hyperparameters learned by Minibatch SGD generalize to test data sets. So we call our method SGGP, which consists of two steps. The first step is to use Minibatch SGD to estimate the hyperparameters given a training data set. And then the second step is to perform prediction using all the training data and also the hyperparameters learned by SGD. So for each data set, we consider 10 independent trials, which consist of 60% training data and 40% testing data. We focus on the RBF kernel, and the mini-batch size for mini-batch SGD is set as 16. We use nearby sampling, and for all the algorithms, we perform 100 epochs or 100 iterations, depending on whether it is a stochastic algorithm or a deterministic algorithm. Okay, so first we look at how SGGP performs for these two data sets, which are of size 2 million. What we find is that SGGP only takes about 1 or 2 hours for the training, and that is huge computational savings compared to the previous work, which used 8 GPUs and a few days to train 1 million data points. Here we don't use GPUs, we only have a single core CPU. Okay. So for these previous two data sets, the size is too large, and we cannot apply other state-of-the-art GP methods using our computational resources. To facilitate comparison, we also look at some smaller data sets, and we compare SGGP, our algorithm, with the other three state-of-the-art methods. EGP is exact Gaussian processes, which utilizes GPU to accelerate the optimization procedure, and they use all the data points. And SGPR and SVGP are based on inducing points. And what we find is that the SGGP is not only leading us to significantly faster training, but also lower prediction error most of the time. So the green values here means the smallest value across different methods. Okay. So in conclusion, we find that SGD can still be a very promising tool in correlated settings, such as Gaussian process model selection. So we have convergence guarantees for mini-batch SGD in this setting, and we also show promising performance of mini-batch SGD in simulations and benchmark datasets. And there are also some open questions in this direction. For example, currently we only have the convergence guarantees for learning the two variance parameters, sigma f squared and sigma epsilon squared. But sometimes it may also be of interest to learn some parameters inside the kernel function, such as the length scale parameter. The length scale parameter inside the RBF kernel. Actually, in our numerical experiments, we have tried learning this length scale parameter, but and it works really well, the mini-batch SGD, but we don't really have theoretical guarantees for now. So that is the gap we have between the theory and application. Second, when people don't really know what kernel is the appropriate one to use in the covariance function, it might be appropriate to consider a linear combination of multiple kernel functions. And then we can put a scaling factor for each kernel and optimize over that scaling factor for each kernel. This setting is actually an extension of the model that we are considering in this work. So it would be of interest to see if our results is going to extend to that case. And the third question is that although we already have some heuristic arguments to understand why nearby sampling is doing well for the convergence of the noise variance, it might also be better if someone can come up with the rigorous convergence rate for these two sampling schemes, so that we have a deeper understanding of what is going on there. So that is all for my talk. Thank you for watching, and if you're interested in our work, you may also, if you're interested in some more details, you can check out our paper.